Okay, so the last thing we want to do is we want to look at a special type of linear transformation that will apply a change of basis. Okay, this is the function of this linear transformation. And we'll show briefly how it can be applied to principal component analysis, what the basic idea behind principal component analysis is. So here's our basic problem, is that we're going to start off with some finite dimensional vector space. Let's just say it's Rn. We're usually working in the Euclidean basis, so if we have some vector, we could rewrite it as follows. And of course we could factor out, and we'd end up with a linear combination of the basis vectors. Okay, which is all fine and good. Except sometimes we'd rather work in a different basis. So the question is, what would this vector be if we changed the basis to something new? And we saw before that the basis is not unique for most vector spaces. How would we do that? Okay. Well, here's kind of the motivation, and I'll give you a simple example, and we'll show how to do it in the process of solving this example. A very common situation where we want to make a change of basis is where x and y are bivariate normal random variables. And let's just suppose that the means of both of them are 0. And so in this case, we know that the PDF for the random variables looks as follows. This is the joint PDF for x and y. And notice we have this sigma to the -1. Well, this is actually the inverse of the covariance matrix. Okay. And let's just suppose, for the sake of argument, that this is a covariance matrix for a particular, bivariate normal distribution. Notice that there's problems with this. X and Y are correlated. Notice that the covariance is not 0. Okay. It's also not clear which random variable is contributing more to the variance. Okay, and we'd like to know that when we're trying to control a process. We want to know which random variables to kind of control as to minimize the variance. And so the solution is a change of basis. We're going to show that we can make a change of variables to a new coordinate system where the vectors are still orthogonal, but they're uncorrelated. And in the process, we're going to be able to show how each random variable in the change of basis contributes individually to the variance. So this is very useful to be able to do. And let's see how to do it. So how do we make a change of basis? Well, the idea is we're going to use the eigenvectors of the covariance matrix. So we do this by first finding the eigenvalues. And the basic idea is, the reason why the eigenvectors are a good candidate is, notice that when you multiply the covariance matrix by that vector, you get back the vector. So it's not mixing up the eigenvectors, okay, in a sense. So we have a clue that this is the right way to go. Now, there are 3 very important things about eigenvectors. And the first is that eigenvectors corresponding to distinct eigenvalues are orthogonal. It's very important. And you can prove that. It's not hard to prove. The second is that whenever we have a symmetric matrix, and you notice our covariance matrix is in fact symmetric, we can always make the eigenvectors orthogonal. We can always find a set of orthogonal eigenvectors, and that should be EVR, not ERV. Okay. And the last and important thing is the fact that the eigenvectors for a real symmetric matrix are always real. In other words, the imaginary part of each eigenvalue is 0. Okay. So here's our approach. We're going to find the eigenvectors of the covariance matrix. We're going to make a change of basis from the standard Euclidean basis, to the basis that is the eigenvectors of the covariance matrix. It makes sense to do this because notice that the eigenvectors are going to be orthogonal since the matrix is symmetric, and there's going to be n of them, and therefore they're going to span Rn, so they can be a basis. Okay. And now we're going to look at the covariance matrix in this new basis. We want to see what it is after we make this change of variables. And what we're going to see is it's going to look as follows. It's going to be a diagonal matrix. But we're going to show this, okay? We're just claiming this, that these are going to be the benefits of making this particular change of basis. And you can see here that the covariance is 0. It doesn't mean it's uncorrelated, but we know that the two eigenvectors are going to be we know that the two random vectors, which are going to be the eigenvectors, are uncorrelated because they're going to be orthogonal. Okay. All right. And of course, what's going to happen in the end is when we go back and we re-express the joint PDF, notice that it can be factored in such a way that this shows us very clearly these two random variables have to be independent. Okay? All right. How do we do this? Well, let's go ahead and find the eigenvectors and eigenvalues first. We'll find the eigenvalues initially, and I'll let you go through the mathematics. You can verify this, but you'll find out the eigenvalues are 1/2 and 3/2. Now we're going to want to find the eigenvectors. Well, we go ahead and we just solve the following linear system of equations. And when we do, for the two eigenvalues, we get the following two eigenvectors. And notice that I've normalized them. V1 and V2 are unit vectors. We want that, okay? And so now we're going to ask ourselves the following question. We're going to want to transform the random vector in the Euclidean basis to our eigenbasis. And we're going to call T the transformation matrix, okay, that does that. So notice that if we express some vector W in the standard Euclidean basis, it has some form, okay? But that same vector written in the eigenbasis is going to have different components because it's going to have different basis vectors, right? Okay, so now let's see how to do this. Well, the real question we want to ask is, what is a vector in the Euclidean basis in the eigenbasis? Okay, that's going to be the clue to helping us figuring out what the form of this transformation matrix should be. So now we're going to go ahead and construct this matrix. And the claim is that when this matrix operates on a vector in the standard basis, which should be B, not A, it's going to give back the form of that vector in the eigenbasis. Okay, that's the basic idea. And there's two ways to construct this matrix. I'm going to show you both ways. The first is to make an observation that when we're in B tilde, V1 is the unit vector. Okay, it's the vector 1, 0. Okay, because what does the vector 1, 0 mean? Well, it's the vector that has 1 along the V1 coordinate and 0 along the V2. Okay, and V2 in B tilde is also 0, 1. And you notice that it's not difficult to figure out that the way to do that is just to multiply by the unit vectors, okay, in this matrix like this. This is guaranteed when it multiplies V1 to give 1, and when this multiplies V1 to give 0. And conversely, when it multiplies V2, it's guaranteed to give 0, 1. Why? Because these are orthogonal. Okay? And so this is kind of the general idea. Okay? We can take the standard basis vectors, form the inner product, and this is what we're going to get. Okay? Oh, there's actually a formula. There is a formula that says if we write the standard basis in the B tilde, okay, coordinate system, the b tilde basis, this also performs the same transformation. And you can convince yourself that in fact when this will give us the same as this. Okay. And so basically this is really saying that we're looking at the transformation of the first standard basis vector. This is what it's going to be. This is basically the standard basis vector in b tilde. This is the transformation of the second standard basis vector in b tilde. This is what it is in b tilde, etc. And these will give the same thing. You can convince yourself of that. Okay. Now there's a problem though. We don't just need to convert the random variables, or the random vectors in this case. We also need to convert the covariance matrix, because right now the covariance matrix is in the standard basis. So we have to do a change of basis from b to b tilde. The last thing there should be b tilde. Okay. And there's a formula for doing that. Basically it says you take whatever the matrix was in your original basis and you multiply it by the transformation matrix as follows. Okay. And so now we're going to go ahead and do that. We're just going to put in what our transformation matrix was, what our covariance matrix was, and you notice, just like we said, the covariance matrix in the eigenbasis now becomes a diagonal matrix. Okay. Oops. I put in a 0 there. Okay. So let's put all this together. What good is all this, right? Let's look at the big picture now at what we've done. And this kind of tells you a lot of what principal component analysis actually does. So what we're doing is we're taking the covariance matrix in the standard basis and we're converting it to the covariance matrix in the eigenbasis. And when we do that, we notice that now we have a nice clean expression. Okay. And when we actually work out what this variance is, we notice that we have this nice formula now. Okay. This is not so obvious what this is. This is some sort of quadratic form, but this we know is the formula for an ellipse. And sure enough, when you graph this, you find out it's an ellipse that looks like this. And the advantage to doing this, other than the fact that it makes the problem look pretty, and theoretically it's easier to work with uncorrelated random variables, is the fact that we can tell which components contribute which to the variance. We can see that V1 contributes more than V2 to the variance, and this is useful to know. So that's just one application of a change of basis matrix.